Okay, let's get started with part 3 of 2A ANOVA. Got a little bit of my voice back here. We'll see how long that lasts. And let's switch over to the right screen. Let's see. Here we go. Okay, I think we're ready to go here. Let's talk about interactions and post-hoc tests now. You need to be able to interpret interactions. This is critical for 2A ANOVA. As a matter of fact, it's maybe the most important thing for 2A ANOVA is being able to interpret main effects and interactions, but main effects are a little easier to interpret. So a statistically significant interaction effect means that the effect of factor A on the dependent variable depends on which level of factor B you're looking at, or the effect of factor B depends on which level of factor A. Either one is equivalent. They're both equally valid, but one sometimes makes more sense than another, or one sometimes fits a certain kind of a research question that you might have. So, yeah, good. So, I'm going to leave this here for you and let you think about it while I get a cough drop. So we're not going to go into too many details, but in a one-way ANOVA, we have sum of squares between and sum of squares within. The sum of squares within is an estimate of error, or residual, or random variability among points, right? Well, we still have that error business in a 2A ANOVA, but now we have 3 sum of squares betweens. And actually, the sum of squares add up. Just numbers add up. And this is one of the reasons why we like variance. Variance can be partitioned. It can be divided up into chunks, and it adds up into neat little chunks. So the between and the within add up to the total variance, and the different portions of the between groups variance add up to the total between groups variance. So in this particular case, the total sum of square between is these 3 pieces of the sum of square between. So it would be 921.1 or whatever it is squared, test score squared. It's not critical, but it's good to remember that so that you can interpret the tables, and sometimes you can spot some errors in them. So when we talk about ANOVA, we interpret each statistically significant effect. Statistically significant means that for its F ratio, the p-value that went with that F ratio was less than whatever your alpha was for the test. If it's not statistically significant, then you act like it didn't happen, like nothing happened. So statistically significant, or it didn't happen, right? You act like it's 0. You don't actually say it was 0 because you know it wasn't 0, but you just say there was no significant effect of such and such. And there's a good reason for this, because the result of this test tells us that as far as we're concerned, we have no evidence that it's not 0 in the population. And a critical part of interpreting this is that interaction effects are more important than main effects. So strangely, we look at the interaction effect first to find out if it is significant, and then look at the main effects. If the interaction effect is not significant, then we interpret the main effects as if there were no interaction. But if the interaction is significant, we have to interpret it first. And then if there's any statistical significance to the main effects, then they're secondary. They're kind of leftovers. Now, the way we spot a significant interaction is really, really easy. Non-parallel lines in a graph. This leads us to question 8. Can there be a statistically non-significant interaction effect if the lines on a means plot are not exactly parallel? So I've told you that non-parallel lines mean that there is a statistically significant interaction, or there is an interaction, and then you have to test it for significance. But can there be an interaction effect that's non-significant if the means plot lines are not quite parallel? Okay. So with 2A ANOVA, we can do post hoc tests as well. and we follow a very similar process for one way. The F ratio is the gatekeeper, but for each effect, because you have 3 F ratios. And the significance test of each F ratio determines whether you can do post hoc tests for the means contributing to that particular F ratio. So if one of those effects is statistically significant, then you can do post hoc tests controlled with HSD or LSD or Chaffee or Bonferroni or other Tukey tests or whatever. And you can do them for all the paired means, all the different pairs of means of the levels of that factor, as if the other factor didn't exist. And I'll show you what that means in a minute. We will use the marginal means. And if the F for the A by B interaction, the two-way interaction, is statistically significant, then you can, if you want, do post hoc tests of the differences between all individual cell means. You don't usually want to. That doesn't make much sense in most situations, but you could. And again, you control your family-wise error rate with HSD, Bonferroni, LSD, Chaffee, one of those procedures. One of the problems is that there's often many, many comparisons, and those procedures will kind of kill your statistical power, your ability to find significant differences, increasingly for the increasing number of comparisons that you do. Another problem here is that you might not be prepared to try and interpret the differences or the pattern of differences. What does it mean that this cell is different from this diagonal cell over here, but these two aren't? I mean, it gets really confusing sometimes. So it's much better to do planned comparisons, have theoretical reasons for which comparisons you will make and which ones you won't. So Tukey's HSD or any other kind of post hoc test, you do it just like we do for one way. No, you just kind of expand it to the two-way situation. Let's look at the first effect, the effect of educational method. That was statistically significant. Therefore, we can do post hocs with the educational method means. So these are marginal means. These aren't the means of the individual cells. These cells collapsed, like their average, and the average of these two here, and the average of these two here, and the average of these two here. So these are marginal means. So we can compare lecture to multimedia and multimedia to self-directed, etc. We can do all these comparisons if we like, all 6 of them. The effect of the second independent variable is also statistically significant. So we can do all possible comparisons between means there, which is ridiculous because there are only 2 groups, only 2 levels of instructor degree. We don't need to do anything because the F test of this being significant tells us that those 2 things are statistically significant, which is what we would do with the T test. It would be redundant and pointless and maybe a little stupid to do that. Not that people don't do it from time to time, but it's pretty dumb. If the interaction term is significant, then we can go every which way and compare all these cell means to each other. But there would be a lot. There would be 24 comparisons with 8 cell means. And we might not be able to understand what they all mean. So it would be better, even in a post hoc situation, to only make the comparisons that make theoretical sense to us, that we know we're going to be able to interpret. So in summary, the T ratio is limited. F ratio allows comparison of 3 or more means. Oh, forget about table D. We're not doing that. And we can extend ANOVA to studies of more than one factor. The end.